Hello everyone, I am Meenu Pandey, Assistant Professor Physics. My today's video is on atomic force microscopy. This is a little bit advanced video on this topic. So this is the schematic of AFM. What happens here? A laser falls over the cantilever beam which move over a surface which you want to scan, and after deflecting back from the cantilever beam it falls over a photodetector. The signals from photodetectors are sent to a electronic circuit which process its data, and then with the result which the data gives, it moves the piezoelectrodes in X, Y and Z directions, which helps in the result transformation, and as a result of which a AFM image is obtained. So this is a force distance curve which shows three regimes. First one is non-contact regime, second one is the contact regime, and in between the contact and non-contact regime there lies the intermittent contact regime. So what is the advantage of all these regimes? The AFM work in these three regimes. On the right hand side of the figure you can see the images of the AFM cantilever, how it deforms or how it get deflected in all the regime. The intermittent contact mode is also called tapping mode, where a cantilever beam move between contact and non-contact mode. So these are the few most common imaging mode of atomic force microscopy. These are tapping mode, Kelvin probe force microscopy, which is also called KPFM, magnetic force microscopy, which is also called MFM, and the last one is conducting AFM, which is also called CAFM. The most common type of AFM probe which are used is first one is silicon tips, or the second one is platinum iridium coated tips, which is used for either KPFM and conducting AFM, while the third one is cobalt chromium coated tip, which is used for magnetic AFM. So this is a image which shows a AFM cantilever. The length of a AFM cantilever is about 100 to 500 micron, while the tip is about 5 micrometer tall and its diameter is about 100 nanometer. So it is used to find with the help of this tip we can get a resolution of about 20 to 10 to 20 nanometers. So first coming to tapping mode, with the help of a tapping mode of AFM, you can easily able to get the surface topography, and you can do tapping mode scanning over a conducting surface, a insulating surface, or even a semiconducting surface. And when further using your software you analyze the data, you can easily able to find from it the depth, power, spectral density, the roughness of your surface. You can easily find a step over your surface, and even you can see the 3D profile of your surface. So on the right hand side you can see two images. This is a annealed TI thin film on a silicon wafer. So the first one is a 2D image which we obtain through the tapping mode scanning by an AFM tip, and further by analyzing the data through the software we can able to see its 3D image. In KPFM, the first common thing which you can do is you can easily find out the surface topography, and in the second step you can find out its surface potential and work function of the surface for which you are doing KPFM. But one thing you have to keep in mind, that the surface potential of the surface should not exceed plus minus or minus 10 volts. So how the AFM work while do a measurement for either KPFM or MFM, it's do scanning in two ways. First, either it do a surface scanning in contact or tapping mode, and then it shifts itself a little far away from the surface, means in far field, and do a scanning for either the KPFM or magnetic force microscopy, because both the forces are a far field forces. On the right hand side you can see two images um, for a magnetic force microscopy scan. So the first image of this is a AFM scan done over a magnetic disk. So the first image shows just the surface topography, which is done using either tapping mode or a contact mode AFM. While the second one is the magnetic force microscopy image of the same surface, which easily shows the magnetic domain present over the surface. So this is the power of a atomic force microscopy in advanced mode. Similarly, you can do a conducting AFM. So what happened in a conducting AFM? Voltage is applied on the tip of a cantilever. So first, we do a normal surface scan so that we can see a surface profile. This surface scan is done either in tapping mode or non-contact mode. So the on the right hand side you can see two images. So the first one is the topographic image of a surface, but in the second when you do a second scan, you apply a voltage to the cantilever, and then you do the surface scanning of the same surface, and you can see that all the portion is black except two strips. So the two strips are bright because they are conducting in nature, while the other one is black because there is no conductivity. So this is the power of a conducting AFM, where from the same surface, after seeing the surface topography, you can find the conducting region. So thank you. This is all about today's lecture.